Welcome back. Let's do a small example to make these concepts maybe a bit more clear. See if I can make some space. So let's say instead of our standard really fading channel, we have a discrete SNR distribution. Zoom in here. So gamma and P of gamma. And gamma can take on two values, 0 and 10, let's say, with probabilities like this. Let's say probability Q and then 1 minus Q. And then the error probability, the symbol error rate is as follows. PS of gamma is equal to 0.5 when gamma is less than 5, and 0 when gamma is greater than 5, just as an example. Now the question is, what is the average error probability, PS bar? Now since things are discrete, we no longer have an integral, but rather a summation. So we'll have a summation over all gammas, P of gamma, PS of gamma. So we then plug in all possible values, P of gamma equal to 0 times PS of 0 plus P of gamma equal to 10 times PS of 10. Okay, and the first one is Q times 0.5 plus 1 minus Q times 0. So I get Q over 2. So you see here that you are really limited by this worst case channel. It doesn't really matter how good the good channel is. If the bad channel is really bad and it happens often enough, even if Q is not very large, you're really limited by this channel. So even if Q is 0.01, so 1% of the time, then your average symbol error rate will still be 0.005, right, which is very far away from 0. Now, an issue with this average symbol error rate is that it goes over an infinite interval. And this makes it, in most cases, hard to compute, except in these special cases such as BPSK. So we will soon see how to solve this integral over an infinite domain. But first, let's really look at what this means and compare with the additive wide Gaussian noise channel. So you recall for the additive wide Gaussian noise channel, then PS is equal to some Q function. I don't remember the arguments now, but basically something that goes down very quickly with the SNR, right? So now we want to contrast these two expressions, and this is what is done here. So on the x-axis you have your SNR gamma b, which is equal to gamma s expressed in dB. On the y-axis you have your symbol error rate, PS bar, which in this case is equal to P bar. The average symbol error rate is equal to the average bit error rate because we have BPSK. And then we have two curves. The one in the bottom, this is for the additive wide Gaussian noise channel. And this here is for our Rayleigh channel. Right, so this here is approximately 1 over 4 gamma b. And what you see, well, you can interpret this curve in two ways. So you can, for instance, draw a line like this. And then you see that for the same signal to noise ratio, or the same average signal to noise ratio, this is actually like this, average SNR, you see that you do much worse in the really fading channel than in the additive wide Gaussian noise channel. You could also look at it in another dimension, like drawing a line like this. And then you see that to get the same symbol error rate of the 0.01, you need 52 times more power. Right? So you need to transmit with much more power to reach the same performance. So overall, this is very bad news. Communication over the wireless channel is much harder than communication over the additive wide Gaussian noise channel. Now, we've only are able to compute this average error probability for BPSK. There's a numerical technique to compute it for other constellations. And then how do we do this? So how do we compute, at least numerically, integrals over an infinite domain? Now, when the domain is finite, you can use this standard approach where you just divide up the domain in different small bins and evaluate the function at those bin values and sum over all the bins. When the domain is infinite or finite and the problem is kind of nice enough, you can use this thing called Monte Carlo integration. Right, where you want to compute this integral here, I. And the way that you do this is you generate samples from a distribution and evaluate the function as 1 over the number of samples, sum n from 1 to n, e to the power minus xi squared over 2, where xi is samples from this uniform distribution. So that's a way to numerically evaluate this integral, but it depends really on the structure of this, what's under the integral, then that you can do this successfully. Another approach is to do a symbolic transformation of the integral. So here is just an example where you have something with an infinity here, and by doing some mathematical transformations you obtain a finite range, and then you can use any kind of nice technique from numerical integration to solve this integral. So the next few slides deal with one of those transformations. The way that this is done is it built on something called the moment generating function, which you may have seen in some probability class. The moment generating function is basically the Laplace transform of the distribution. So if you have a random variable x with distribution p of x, and you compute the Laplace transform, so this is given by this expression, this is the Laplace transform, this is the compact expression, you have a function that depends on this new argument s, and this is called the moment generating function. It is called the moment generating function because it has this special property. If you take the moment generating function, you take derivatives with respect to s and set s to 0, you obtain the moments. Now recall these moments are defined by integral x to the n px x dx. So that's why it's called moment generating function. Now we can compute the moment generating function of any random variable. In particular, we can compute the moment generating function of the SNR. And it turns out, as you've seen for instance, for Rayleigh and Rissian fading, this has also some exponential. Right? This has some nice form which allows a closed form expression of this moment generating function. And these are given here. This is the moment generating function for Rayleigh and Rissian fading. And this we can then use to numerically solve these integrals. So this is what we'll do now. Sorry. So we start from our moment generating function. This is our average error probability. We've seen that the average error probability can be written with a Q function. This is from this table earlier in the slide. There's also, it turns out, an expression for the Q function, which is known as Craig's formula. So this is this expression for Q function. We substitute this in here, then we substitute this in there, and then we end up with this expression here. Okay, so this is exactly the same. And now I will highlight some of the terms. So we have this integral here, this exponential with the parameter gamma, p of gamma d gamma, and then this thing here I will call s. And if you now look at the definition of the moment generating function, here, you see that it's identical. So then you can plug this in and you obtain the moment generating function evaluated in this value of s, and then you integrate over this additional variable phi. And the nice thing now is you have finite domain here, and then you can compute this very easily numerically using your favorite numerical integration method. Okay, so this is just a technique to compute average error probability. Finally, you can also combine the randomness of shadow fading and multipath fading, which is done in this slide. So let's suppose that you really care about average error probability, so you have some fast fading channel, but you only account for this when the SNR due to path loss and shadowing is high enough. So basically you have like this. Oh, it's not a very good color. You have gamma S and dB with the bars. This is after path loss and shadowing. This is something Gaussian, right? If you are below some threshold, you say this is outage, right? When this gamma bar S is below some threshold, and this here is gamma bar S and dB. And then when you're not in outage, right, which is in this regime, then you care about the average error probability. So there's two sources of randomness. You have the log normal distribution due to shadowing, and then in addition you have the average error probability due to the multipath fading. So to make this more clear, let's look at an example. Suppose you want to do a BPSK over the really fading channel. So remember that for BPSK, the error probability is 1/4 gamma, right? The bar. You have shadowing with 8 dB standard deviation, and you want to have an average SNR below 10 to the minus 4 most of the time. So 99% of the time, you want to have this average SNR. So you want to have an average symbol error rate below 10 to the minus 4. And now this is your task. How should we set the SNR due to path loss only? Sorry for all these messages. To achieve this target symbol error rate 99% of the time. So it's the combination of really fading and Ricean fading. So I recommend you pause the video and try to solve this. Good, let's see here. Sorry. All right, so given path loss only, the SNR will vary due to two effects, shadowing and multipath fading. So let's look at a function over time or space. How this SNR due to path loss and shadowing varies given this SNR due to path loss only. And this is really what we want to set. So we want to adjust this level up or down. Given this level, which gives this red line, we have the SNR due to shadowing on top of that. So this is this Gaussian random variable on top of that. Okay, and we want to make sure that we meet this average symbol error rate. Let's see, what was the requirement? Average symbol error rate, 99% of the time. Good, so we want to make sure that gamma bar S is such that the average symbol error rate is 10 to the minus 4. And this should be achieved 99% of the time. So to get 10 to the minus 4, we can check this figure here. Let's go back. 10 to the minus 4 goes here. Oh, further. We go down. So this is about 34 dB. So we need gamma bar S to be 34 dB. This is the SNR due to path loss plus shadowing. And we want to have this 99% of the time. At least 34 dB. Good, we go back. All right. So we want gamma bar S to be at least 34 dB, 99% of the time. So we can write this now in this expression here. Gamma bar S after path loss and shadowing should be below 34 dB, less than 1% of the time. And now, since this is a Gaussian random variable with known mean and variance, we can use the Q function to express it like this, which gives us this expression. So we find that the SNR due to path loss only should be more than 52.6 dB. If this is true, right, then given the shadowing standard deviation, we will make sure that we are above 34 dB 99% of the time. And then there we will have our average symbol error rate of 10 to the minus 4 by construction. So this is a bit more involved example, but at least it combines these two randomness notions. We have one more topic left, which is non-coherent communication. Non-coherent communication is used when the channel is varying too quickly to really track it to provide coherent communication. To understand this, let's look at a simple model here where we have the received data, the received observation, RK. ZK now denotes our channel, which changes over time. This here is the data. So we use PSK, so everything is on the unit circle, and then we have noise. In standard coherent communication, which is what you've seen so far, is that we encode information in the phase, right? So we have our constellation, oops, like this, like this. So we have our constellation points, and then we have bits 0, 0, 0, 1, 1, 1, 1, 0. And then depending which bits we have, we just send the corresponding points from the constellation. Then it goes over our channel and we add noise. And let's suppose that this channel does not change over time, right? What we can then do is we send a data packet, which looks like this, where here we have all our data. And this here is a pilot. And this pilot is known to the transmitter and receiver. This pilot allows us to estimate the channel, because then we have an observation, right, where we know R, we know the data, and we want to figure out Z. So that's an easy problem. So then we can estimate the channel, and again, we can make it constant here. Give it the estimate of the channel, and then you look at the later observations corresponding to the data or the payload. And from this, we can easily estimate the data by the maximum likelihood criterion. Maximum likelihood or minimum Euclidean distance, minimum distance. So this is the standard approach. But now, if the channel is changing, then I have a dependence on K here, a dependence on K here, and dependence on K here. Then when the channel is estimated at the pilot in the beginning, by the time the data comes along, the channel will have changed. So you cannot do this coherent communication anymore. Or you should maybe alternate pilots and data and have a lot of overhead due to pilots. So to address this, there's an alternative way to communicate, which is called non-coherent communication, where you don't put the information in the absolute phase, but rather in differences of phase. So how this works is, again, you have your stream of bits. You have your standard modulation, so this part is the same as before. Up to here it's the same. So here you have your MPSK points, MPSK, good. And then you have called differential encoding. And what you do is you multiply the current data symbol with the previously transmitted PSK value. And then you send it, you keep it in a memory, and then you keep going through this loop. So what this means is that e to the power, well, I can maybe write it, theta k is equal to phi k plus theta k minus 1. And you can set theta 0 equal to 0. Okay. Good. Then we go over the channel and we add noise, and then we have our observations, RK. And what we then do is this is this box then, this is differential detection. We process as follows. And we assume that there's no noise, just to make things simple. We generate new observations yk, which are given by the current observation and the complex conjugate of the previous one. Okay, and remember that the first symbol is a pilot symbol. We know what is the first symbol. We plug in the channel, so this is the part of the channel for the two. Then you have this phase difference, and now we can make use of this relation, and we obtain the desired phase again, multiplied by a complex number. Okay, and this is really what can cause trouble. Now, this number here, there are several cases. If the channel is constant, right, then zk is equal to zk minus 1. So this is case 1. And let's call this number A. Okay. Then A is real and greater or equal than 0, right, because the complex conjugate wipes off any phase. So this is good. In the second case, when zk is approximately zk minus 1, so let's say that zk is rho k e to the power j psi k, and zk minus 1 is same rho k e to the power j psi k e to the power j epsilon k, where epsilon is a very small phase, right? Then A will be rho k squared e to the power minus j epsilon k. So if I were to draw this on the unit circle, it will be some value here. So it's almost real. So that means A is approximately real, greater or equal than 0. There's a last case when the channel is varying very quickly, then it can be any complex number, right? So this is the third case. Then A can be anything. And then you cannot communicate. So here you can communicate, here you can communicate, but in the third case you cannot communicate. So this means that even in the absence of noise, there will be an error floor when the channel is changing very quickly. So in other words, as a function of signal to noise ratio, and we compute the average error probability, there will be an error floor, so that no matter how high the SNR, you cannot beat it just because you will be limited by this effect at some point. And it turns out that you can analyze this exactly. So the average error probability for differential binary phase shift keying, so this is when you do BPSK with this scheme, is given by this expression where you have a value rho, and this value rho depends on the autocorrelation function. So the autocorrelation function after one symbol versus the autocorrelation function at 0. And for the Jake spectrum, you can compute this exactly just by plugging this expression into the slides from that lecture. So now we can evaluate this, and then we get something like this. So on the x-axis, you have the average SNR due to path loss and shadowing. On the y-axis is the bit error rate or symbol error rate. And then we have different curves. So the blue curve is when there is no mobility, so the channel doesn't change. And in that case, well, you will have this kind of performance. So that's a bit similar to Rayleigh fading. When the channel changes, you will have an error floor. So no matter how high the SNR is, you're limited in terms of performance. And this error floor will go up when the velocity increases. Right, and at some point, if the velocity is too high, your symbol error rate will just be very high all the time, no matter what the SNR is. So I would say that this differential phase shift keying is not used very widely, but it's something that you can consider when you have a quickly changing channel and you have no way to track it otherwise. Good, this brings us to the end. So we've seen different notions of SNR, different notions of power. We've computed bit error rate and symbol error rates. We've computed outage and average error probabilities. We've seen the differences between coherent and differential detection, and we were also able to explain why differential phase shift keying has an error floor, meaning at very high SNR you're still limited due to the fast fading. Good, then see you next time for lecture 6.